Okay, for those of you watching, the first part of class just did not work. I lost the clip. So, fortunately, I haven't done very much. So, I have to quickly summarize this board. So, we're getting into first order equations of this form. It's a general first order linear equation in one space dimension, so we have space and time. We're solving an entire real number line, so there's no boundary condition. This is our initial condition. And we're going to solve this by changing variables from x to t to these variables, tau and s. And I want to point out a notation difference. In the 606 text, they use t and s. I refuse to use t here because the book uses x and y, which is totally non-intuitive for these kind of problems, which are often used to model time-dependent phenomena. So I'm insisting on using t here, and I'll use tau in place because it's pretty close in appearance. Those of you who have taken 517, they switch the order, but the rest of you, you can forget about that. But just want to make you aware of the notation difference between my notes and the 606 text. Okay, recording seems to be going much better now, so now I remember to not upload anything until both classes are done. And that's, so unfortunately we've lost some time, but I think we'll still get through everything. Okay, so what I do is, so I'm going to obtain new initial value problems from the original. Okay, so dx d tau is equal to the coefficient of du dx, a of xt. And the initial condition is equal to s. Okay. So in fact, we're really solving not just a single initial value problem, but a family of initial value problems, because s is also a variable. So for each value of s, we have a new initial value problem, but we're going to solve them all at once. So our answer is going to be in terms of s, our solution. Okay, and it's similar for y, t. dt d tau is equal to the coefficient of du dt, so b of xt. And its initial condition is 0. And the reason for the initial value being 0 is because our initial time from our initial condition is 0. So the initial value comes straight from this. So this is describing, so these initial conditions describe whatever the initial curve is in your original initial value problem. Now, in our case, the initial curve is just the real number line, x goes from minus infinity to infinity, and t equals 0. So we're using s as a parameter along the real number line, along the entire x-axis, and then t is a 0. Okay, now this next equation will explain why I'm using these ODEs here, because now I need to focus on solving for u. So I have a of xt du dx plus b of xt du dt plus c of xt u can be written as, because a of xt is dx d tau. So this is partial of u with respect to x dx d tau plus partial of u with respect to t, and then b is dt d tau. And then I still have this being the same thing. And that equals 0. So this is a chain rule in action. So I have du dx dx d tau, du dt dt d tau. you can think of the x's and t's canceling, if you will. Now, some particularly anal retentive mathematicians would shoot me for saying that, but let's face it, it works. So this whole thing, I can simplify to du d tau. So that's what all of this is. If I just condense it by using the chain rule in reverse. So du d tau plus c of x t u is equal to 0. So now, this equation and these equations, I can now solve. Now, before I forget, I also have an initial condition, u of, S0 is equal to f of s. I should mention I have these accidentally switched in my notes. This is a correct order. Okay, so and that's why s is kind of playing a role of a spatial variable. Tau is kind of playing a role of a time variable. So now we have three separate initial value problems to solve. But the thing is, before I had a PDE. Now I have three families of ODEs. And for many problems, like the examples I'll show you, these are generally quite easy to solve. And then by putting all the solutions together, we can get our solution to our original initial value problem, u of xt. Because that's still the goal here. Okay.
I have a question.
Yeah.
Where'd you get the u of s is comma 0 equals f of s? Would you do that again?
This comes from the initial condition of the original problem. So, but instead of x, I'm using s.
Okay.
Yeah, because s is used to parameterize the initial curve. Now, in this case, the initial curve is just the x-axis. So on that line, t equals 0, x and s are the same thing. Now, for more complicated problems where you have a more complicated initial curve, then it's a more complicated relationship between s and x and t.
Meaning there's boundary conditions.
Well, still an initial condition, but you might be, here we're dealing with a very simple domain. We have the entire real numbers and then t greater than 0. So just see like the upper half xt plane.
Right.
But you might have a more complicated domain than that. There's still a well-defined initial curve. You could think of it as a boundary, except we're treating this as an initial value problem, not a boundary value problem. So, all right. So the method of characteristics. Which I will illustrate momentarily. Has these steps. So first you solve for x of tau, t of tau, and u of s tau. So you go ahead and solve these initial value problems. I should say solve for all three of these things. So you solve these three box initial value problems. And then you change variables back. Because now you're working in variables tau and s, and you want to go back to x and t. And you want to do this in your solution u, because after you have this, you have your solution u, but it's in the wrong variables. It's in s and tau. You want to express in terms of x and t. But that's what these are for. So you can use these to figure out how to change back. So that's why it actually makes sense to solve one problem by solving three. Because those three problems are a whole lot simpler. Okay. So this idea of method of characteristics, it's used to transform your PDE for u into a simpler ODE. But the way that's done is to define these characteristic variables in order to set up this condensing of the equation in terms of the using the chain rule. Okay. Now, all right. So I have some examples that I'll use to illustrate the method. All right, at least this time taping is going smoothly for once. Okay. All right. So for my first example, I have du dx plus du dt plus 2u is equal to 0. And my initial condition is sine x. Okay. So in other words, a is equal to 1, b is equal to 1, and c is equal to 2. So those are my coefficients. Okay. So my initial value problems in my characteristic variables we have dx d tau is equal to a, which is 1. X of 0 is equal to s. Okay. And then we have dt d tau is equal to 1. T of 0 is 0. So that parameterizes the initial curve. And then we have du d tau plus 2u is equal to 0, and then u of s0 is equal to sine s instead of sine x. Okay. So now we can go ahead and solve these. So, for instance, for these, we can carry out integration with respect to tau, because my right-hand sides here don't depend on x or t at all. So anytime you have a function of only tau here, or maybe even a constant, you can just integrate both sides. So, so what would x of tau? Well, I'll just write it as x. So what would x be equal to? Tau. But don't forget the initial condition. Plus s. Because you want to make sure when you plug in tau equals 0, you get your initial value. So that's s. Okay. And what is t equal to? Also tau here, but there's initial value of 0, so we don't add on anything here. Okay. Now, these define the what are called characteristic curves. Okay. So if you were to, you can plot these in the xt plane. Now, for the meaning of these variables, tau is indicates what's happening along a curve. S is used to identify different curves. So the idea is, just for general characteristics, here's your x-axis, but different s values are used to identify the beginnings of different characteristic curves. And then each of these characteristic curves, with lines in this case, tau is used to parameterize different points along a curve. So this is the meaning of a variable's s and tau, what purpose they serve. So what about these particular characteristic curves? How would you describe these? Well, if you'd asked if you had an equation, like these are parametric equations, so those are kind of a pain to work with. But if you have x and t together in an equation, what is the actual relationship between x and t, just from this?
X equals t plus s.
Yeah, because you can eliminate the parameter tau pretty easily. So you have x is equal to t plus s. So what you can do is, all right, I'll solve this later. I want to draw the characteristic curve. So here's the xt plane, xt plane. So the way this will work is your characteristic curves are all going to be lines where the slope is equal to 1. Okay. Because if you write this in like y equals mx plus b form, t is like playing the role of your y value. So t is equal to x minus s. So that means you have lines that all have a slope of 1, but different y-intercepts. So you just have infinitely many lines, all the same slope. Okay. So what happens is, the way these kind of first-order equations work is, along this is your initial curve, the x-axis, where t equals 0. Your initial data is given along this curve. That's your initial condition. The initial values that are defined on this initial curve are propagated along these characteristic curves. So what's happening is it's just being, in this case, it's propagating to the right. But depending on your original PDE, that describes what characteristic curves you're going to get, and the directions in which your initial data is going to be propagated. Okay. Now, one thing I'll point out when I get to later examples is, this is a linear equation. However, you can use the method of characteristics for nonlinear first-order PDE also. The complication is, when you have a nonlinear PDE, your characteristic curves might intersect. So what happens if you have initial data that's being propagated along these initial curves, so different values starting from different points, and then they meet? That's a recipe for trouble, because you have different values at the same point. The solution is supposed to be single valued, to be well defined. That's called a shock. And I'll talk more about shocks later on, but so this is something that never happens in linear equations. Linear equations, your characteristic curves can never cross, but if it's not linear, they can. And lots of crazy things happen. That's actually an issue in traffic flow that can be described using an equation such as this, where your solution U represents the density of cars at any point along the highway at any point in time. And what happens is you have cars entering and leaving, and as the traffic piles up, this happens actually like in high traffic areas, like Southern California, for instance, where everybody's moving along, there's no accident, nothing like that, and then all of a sudden, everybody slows down, and nobody has any idea why, and it's really irritating.
Because they're idiots.
Um,
Sorry. That's a
No?
great explanation.
It's just traffic.
Okay, and then they start moving again. It's because there's a shock.
Yeah.
So,
That happens all the time.
yeah.
People randomly stop their cars and argue with each other.
But
That's a shock.
I can see that one.
But you don't even need that to happen. It just happens from a changing density, because everything's being propagated along these characteristic curves at a finite speed. That's also why, for instance, like I gave you an example before, where like stop at a red light, it turns green, you have to wait before you can move.
You said
Right.
it's changing density, like more cars entering the interstate,
Yeah.
leaving, and
Yeah, that's what I meant.
oh, well then there's a reason for it.
Well, yeah, but so mathematically, if you model that, that's what's happening. It takes a
Oh.
form of a shock, where you, And so but it takes time for that discontinuity to work itself out before traffic starts moving again.
But there is a reason. Okay.
Yeah, it's not just people being dumb. Well, okay.
In Hardy Street, yeah. People big.
Yeah, Hardy Street people are just talking.
Yeah, well, when I first interviewed for this job, that's one of the first things I discovered about Hattiesburg, how annoying Hardy Street is.
All the traffic.
No.
is just-
If you drive in either LA or DC, Hardy Street is fine. They're all idiots.
I'm
They're just fine.
It, like all of Hattiesburg's traffic is just confined to Hardy Street. It's just.
Yeah, but the thing is,
Why would I ever drive in
this
that?
is a small town compared to most places.
Yeah.
It is like
That's what I'm saying. They're all idiots.
I've driven in bigger
But it's not-
cities, but for some reason people just can't figure out.
They're
Hardy
bigger
Street.
idiots.
Sit 3 hours
Once
on the
you-
Beltway.
in the world.
Move 3 feet.
Okay, what really does annoy me though, here, is when they changed the exit on Hardy Street in 59, when you're going, if you're coming off southbound 59, and they put up new signs indicate which lane to use and so forth, and people just,
Westover Drive,
Yeah.
and then they do the Westover Drive one and then go over
yeah,
because they're all raving lunatics.
yeah, that bugs me because then I have to deal with those people when I'm trying to go home. So, yeah, and they just don't catch on.
Wait, you take Hardy Street home?
Uh,
I was gonna say, why don't you take 4?
it depends
You
what
know.
it
But
depends
it
what
matters what time it is.
yeah, it
If
depends
it's
it depends what time of day.
Yeah, you can't get to.
Because on 4th Street, you have to drive at like 5 miles. an
Yeah,
hour.
around 5 o'clock it's bad no matter what.
Oh, except I'm not like douchebag that like once those 2 lanes start and there's that turning lane, I'm like, and so I just drive the entire
Sometimes it's hard
turn
to
lane.
lane.
Sometimes like a cop, have you noticed that? Like every now and then a cop will be like moving really slow and turn, like 'cause people do that all the time.
Yeah.
Okay, so now to finish solving this problem.
Say there goes to.
That's okay. I think we're still. Let's see. Oh, I have 38 minutes left. I think we're still fine. Okay. We might not finish everything more, but. Okay. So now I have this last problem to solve. Du d tau plus 2u is equals 0, and u of s0 is sine s. So this is a slightly harder equation to solve, but in terms of like 285 terms, it's one of the first ones you learn to solve. So what is the general solution of this? Do you remember from like this is a separable equation. Well, it's a separable linear equation.
Would be 2CE used, right?
I'm sorry, what?
Would be like 2 something e to something, right?
Yeah, there's the
The
exponential.
coefficient.
And the coefficient e to the 2.
Yeah, 2.
-2.
Negative.
Yeah, if you move it to the other side,
Okay.
yeah, e to the minus 2 tau times the initial value, which is sine s. Okay. So now we have the solution, except it's in the wrong variables, tau and s. However, if I repeat those, so x is equal to tau plus s, and t is equal to tau. So that means that s is equal to x minus t, and tau is just equal to t. So you can just take these equations and rewrite them to isolate s and tau, and then you can plug those back into here to get your actual solution. U of xt is equal to e to the minus 2t sine x minus t. And then you're done. So that is the method of characteristics. You define your IV initial value problems and your characteristic variables. Generally, those are easy equations to solve. You solve all 3 of them. And then from your first 2 that explain how x and t relate to s and tau, you invert these relationships to express s and tau in terms of x and t, and plug those back into your u to get your u into the form that you want. Okay.
Is it you?
Yeah, well, that's a U.
The weird looking thing?
Yeah, the
What?
the weird U of XT. It kind of looks like a teardrop, actually.
Little Wayne.
Huh?
Little Wayne.
Are we good now? Okay. Okay.
Yeah,
All right.
Looks like little one.
that's not.
Little Wayne's tattoo.
Oh! His teardrop.
Anyhow,
That's not what I was confused about. I never knew
Okay.
I was looking at something else.
Alright, so questions about this, I'll do another, but,
These are interesting,
yeah,
You would say that.
of course.
okay. So here's another one, this one has a general initial condition, but slightly more interesting, PDE, so xux plus du dt plus tu is equal to 0. So now I have a variable coefficient for c.
Not linear, right?
No, this is still linear.
It is linear.
Yeah.
Oh, never mind.
Okay.
Never mind.
And I'll just have a general initial condition. U of x0 is equal to big F of x. Okay. So our characteristic, our IVPs or characteristic variables are dx d tau is equal to x. It's a coefficient of du dx. And same initial condition as before. X of 0 is equal to s. dt d tau is equal to the coefficient of du dt, which is 1, and t of 0 is 0, so that parameterizes the initial curve. And then du d tau plus tu, well, in fact, I need to say t of tau times u is equal to 0, and u of S0 is equal to big F of S. Because I don't know what t is yet. I will in a moment, but not until I solve this first. Okay, so what is x going to equal? What? Yeah, so if e to tau times the initial value, because this is another separable linear ODE, and that is s. Okay, and then what about t? That's just going to be
Just
tau. Yeah. All right, so now I can put that in here, my equation for u. So I have du d tau plus tau u is equal to 0. So, so what's that going to give me, like first for a general solution?
The e to the just negative. Wait, hold on.
You do the negative
Where am I?
Negative.
tau squared over 2.
Yeah, you integrate this.
I was so gonna say that, but I thought
Okay.
I was wrong.
Well, knock it off. Okay. Times your initial value, which is this big F of S. Okay, so now we have our solution in characteristic variables, but now we have to invert. So we have x equals se to the tau, and t equals tau. So that means, well, tau equals t, of course, and s is equal to, what is s equal to in terms of x equals to?
Over e to the t.
Yeah, which can also be written as
E to the negative.
e to the minus t. So now we can put these into our solution. So u of x and t is e to the minus t squared over 2, big F of s, which is x e to the minus t. Okay. And that is our solution. Okay. That's strange. Something is off here. I'm actually missing notes. How did that happen? Okay. Not sure what to do about that at this point. Well, things I may have uploaded the wrong thing. Yeah. Yeah, 4 pages missing. Okay. All right. My fourth page should be my office.
Any more turtles?
There's one office
Well,
There's cookies.
cookies,
Some bourbon.
bourbon. Bourbon.
This week is halfway.
That's like
Okay, crumbs.
few pieces.
Yeah, there's something up with my printer and my Mac desktop. Apparently, it does not print the last page. That's the second time it's happened. I have no idea. Okay, so all right, so that's relief that that mystery was solved. Okay, so now, having done two linear examples, I'd like to move to a nonlinear one now, so we can see that similar principles apply. And we'll actually talk about traffic flow. Okay. Okay. So, looking at traffic flow, all right, so U is the density of cars on the highway at any point X along the highway at any time T. So it's a straight highway. Okay. And then I have a function f of x and t is the flux, which means cars per minute, or every unit of time, passing the point x at the given time t. So just the rate of cars passing through a point. Okay. So we have a conservation equation that the rate of change with respect to time of the total so we take the density and integrate it over a certain segment of a highway, so we're integrating with respect to x, from point A to point B. Well, it's like when you take density of an object and you integrate it over a certain volume. That's mass. That's density times volume, which equals mass. So here we're looking at the total number of cars in AB at time t, but we're looking at the rate of change of the number of cars at a particular instant. Well, that would be equal to cars per minute entering the segment minus cars per minute exiting the segment. Okay. So that's a straight conservation of cars. Okay. Now, we can express this as, well, first, I can take this time derivative and move it inside the integral. So this is du dt. And then this I can express as an integral also. It is minus the integral from a to b of df dx. So this is the fundamental theorem of calculus again, in reverse, because f is the antiderivative of partial of f with respect to x. Okay, so now I can move everything onto one side. So I have the integral from a to b of du dt plus df dx is 0. And but the thing is, the segment AB is an arbitrary segment. It just holds for all segments. So out pops my PDE, du dt plus df dx is 0. So this is my conservation equation. So like this, what we're seeing here, we're talking about traffic flow, but this kind of equation pops up a lot from just about any conservation law you have. Because here we have some density, here we have some flux. That can apply in many different contexts. So this is a standard form of a conservation equation. But then you need some information about what is F. Like how does F relate to U in order to be more specific. So what I can do is I can rewrite this as du dt plus df du dx is equals 0. So now it's like more like a proper PDE in a way, because we have partial derivatives of u with respect to x and t. So this is a more common form to write it in for solution purposes. In fact, what we're doing now is we're setting ourselves up to be able to use method of characteristics. Okay. In fact, I'll write this as a coefficient, du dt plus g of u, ux, is 0, where g of u is just df du, whatever that is. Okay. So what g is depends on your context. You want to have some idea of how a flux relates to how a flux relates to your solution, your density. So as we can see, this equation here, because your coefficient depends on u, this is a nonlinear PDE. Okay. All right. So what we'd like to be able to do now is see what we can learn about solving this equation using the same method of characteristics. And the fact that this equation is nonlinear versus linear, that's not going to bother us. Well, not until we have a solution. Because the solution is going to have troublesome behavior because it's nonlinear. But in terms of the actual solution process, we don't really need to do anything differently. Of course, the equation might be more difficult to solve like your characteristic variables. But that's a risk you take using the method of characteristics anyway. Okay. Okay, so to try to solve this, for this problem, du dt plus g of u du dx equals 0, and we have an initial condition, u of x 0 is equal to some function phi of x. Okay. So what we get is, okay, dx d tau is equal to g of u of s and tau, because it's a coefficient of du dx, and x of 0 is equal to s, so that part doesn't change. dt d tau is equal to 1, the coefficient of du dt, and t of 0 is equal to 0. So that just means t once again equals tau. So at least that part works out nicely. du d tau, well, we don't have the coefficient c in this problem is 0, so that's nice. And our initial condition, u of s0 is equal to phi of s. So what that means is u of s tau is just equal to phi of s. Because with respect to tau, there's no change. So in other words, whatever value you have on the initial curve is just propagating along that initial curve, unchanged. So now I can include this information up here. And that makes things quite nice. It's kind of weird how I'm actually solving this equation before this one, but due to the niceties of the PDE, it works out that way. So now this IVP simplifies. dx d tau is equal to g of phi of s. Notice, this does not depend on tau at all. So, what is x of tau? Well, so what does x turn out to be equal to?
That times tau.
Yes, so your initial value
Oh,
Yeah.
yeah, S times.
plus this times tau. Yes. Okay. So it's because du d tau is equal to 0. That's why we're able to do this. Otherwise, my right-hand side would still depend on tau, and I couldn't really go any further in solving it without knowing what g is. Okay. All right. So now I can grab my solution. So u of xt is equal to phi of s, but I can rearrange this. S is equal to x minus g of phi of well, let's see, actually, this is equal to u, so g of u times t. So that's how I can invert the transform. So u of xt is phi of x minus g of u t. You recognize this from a homework, don't you? Those of you who've gotten that far.
It was the same setup as problem like 5 or something like that.
Yeah, and yeah. In fact, it was almost exactly the same thing, because you had du dt is equal to like p of u or rho of u times du dx. So I think like, g is equal to minus p. I think that's the only difference. So as you saw in that homework problem, this implicitly describes the solution. So unless g of u is like a constant or something, you can't really solve for u explicitly in this case. So that's unfortunate. But
How do you know that g of, or oh wait, are you saying the whole thing's equal to u or just the 5s is equal to u?
only 5s.
Oh, whoopsie.
Yeah.
Okay.
Okay. All right. Okay. Now, as far as we go without knowing more about the problem.
U of xt is phi of x minus gu of t.
Yeah.
Like, so you substituted u of x0 was phi of x. So u of
Yeah.
x0 would be phi of s.
Yes.
It's there.
Yeah.
So-
And the thing is, since u is independent of tau, I could just call this. Yeah. So this is really just u of S0.
Right. So
Yeah.
then we plug in u of xt is phi of s.
Um,
Because u of st is phi of s.
Wait. Say again.
U of xt is actually phi of s.
Yes.
Because u of s tau is phi of s.
Yeah, because it's not changing with respect to tau. Yeah, so this is an implicit solution. So in other words, if you have values for x and t, you can plug them in here and have u on the left side and try to solve for u using, like, for instance, Newton's method or some other approach. So it's kind of a pain. But we can still try to understand the behavior of a solution even though we don't have an explicit formula for it. Okay. now, because what I can do is, if I let s equal to x naught, so I have my initial curve, which is just the x-axis, and I have a certain characteristic curve is beginning at x naught. Okay. So what I can do is I can go ahead and use this equation, or actually this one right here, and solve it for t. So I can say t is equal to x minus x naught, which is s, divided by g of u, but u is equal to phi of x naught, because that's s. So I have this way of describing, so this is the equation for characteristic curves. Oh, one thing I want to mention, I have not yet picked out homework problems for this chapter yet. I will. Because homework is going to be described by chapter, and we're going to spend a lot more time on chapter 2 and chapter 1. It's a much longer chapter. So it'll be a while before we can really do all the homework problems. But the book makes some frequent reference to the projection of the characteristic curves into the xt, or in that case, xy plane. So that's when you're describing only the equations for x and t as functions of s and tau. In other words, u is not part of the picture. So they kind of think of a characteristic curves as being in xtu space. But a lot of times you want to focus on what's happening in characteristic curves only in the xt plane. That's really helpful for understanding a behavior of solutions. So when I say projection to the xt plane, this is what I'm talking about. When you describe x and t as functions of s and tau. Okay. Now here, of course, we have to assume that g of phi of x naught is non-zero for this to be well defined. Otherwise, the characteristic curve is just going to be a vertical line. So if we go back to here, if g is 0, all we have is x equals x naught. So it's not very interesting in that case. Okay. So what happens is, okay. So our characteristic curve at any point has, since it has this equation. So what I'm trying to draw this in the xy plane. Okay. So it's x-intercept is here, but my slope is basically going to be like 1 over g. But here's the thing. Okay. So the slope of this line, so it's is 1 over g of phi of x naught. Okay. So every characteristic curve that begins at a certain point x naught is going to have this slope. But here's a problem. All these characteristic curves can have different slopes, depending on the function g, depending on the function phi. So there's a lot of possibilities for what the slope can be. So there's no reason why. So if this characteristic curve has a different slope, perhaps a -1, it might intersect. So this is something that can happen with nonlinear PDE that cannot happen with linear ones. The possibility of characteristic curves might intersect. And what happens is along this characteristic curve, u is equal to phi of x naught. Here I'll call this x1. Along this characteristic curve, u is equal to phi, I should be saying phi, right?
Well,
Okay.
it just depends on where you're from,
Okay.
I guess.
Of x1. These values could easily be in conflict. So what happens is the solution fails to become, it's no longer continuous. You actually have a discontinuity. So when this happens, we get what is called a shock. When characteristic curves collide and they're carrying different solution values along themselves, and so what do you do? Like you have this multi-value solution. Okay. Now, so what happens to a solution? At a shock. Okay. Now, okay. Strange notation here. Let me pull it out. Actually, how am I doing on time? I have 8 minutes. Okay. So what happens is the discontinuity that's created by the shock with a speed determined by this slope. Okay, I'll explain this notation in a moment. Now, f is the flux function from before. So this f is the same as the f in the previous board. So u, L, and u, R, those are the values that collided, basically. These values of solution on the left and right sides of the shock.
Is it UR plus UL in the denominator?
What?
You are minus or plus UL.
This is minus. This is a slope.
Right, oh, it has to be.
Yeah. Change in f divided by change in u. So this is like f prime of u in a way, even though it's really an average rate of change, because u is no longer continuous, let alone differentiable. Yeah. Okay. All right. So the solution is still defined; it's just no longer continuous. So before you had these values propagating, and now there's a conflict, so now the discontinuity continues to propagate along these characteristic curves. Okay. The last thing I want to mention in the last, and we're going to revisit this in more detail as we go through the chapter. It's all about non-equations. And then Monday will be spent doing more examples of method characteristics. So you're going to get plenty saturated with this. Okay. But the last thing I want to mention is a complication that did not come up in these examples, but certainly could come up if you're not careful. So one pitfall of the method of characteristics is that you can't always invert from s and tau to x and t. And the reason why is, the s, okay. So the dependence on s comes from the initial condition, because we're always using it to state the initial conditions of these characteristic variable problems. the dependence on tau comes directly from a PDE. So, the thing is, the PDE and the initial condition have nothing to do with one another. They're completely independent. So, you have a given PDE, you can specify whatever initial condition you want. What it means is for any PDE that you have, there exist initial conditions such that the Jacobian of a transformation which is dx ds d dt d tau minus dx d tau dt ds. Now, dt d tau is just equal to the coefficient b, and dx d tau is equal to the coefficient a from your PDE. That might equal 0 if you're unlucky. Which means the change of coordinates is not invertible. Recall from multivariable calculus, this is a Jacobian of a change of coordinates.
Okay, I have a question. Back before, I thought we were. Never mind. I thought we were saying that X corresponds to tau and T corresponds to S, right? Did you do that?
I may have written tau s earlier, but
Yeah, you wrote tau S earlier. Does
Yeah,
it matter?
no.
Okay,
Oh, okay.
alright. Just
Yeah.
making sure.
Yeah.
Just making sure.
T and tau correspond. That's why I use similar letters. X and S roughly correspond.
The order doesn't matter.
No, yeah.
Oh,
Yeah, because if I change the order, that just swaps rows or columns in the matrix,
okay.
and that does not affect whether J is 0 or not.
Okay.
Okay, so when J is non-zero, which is what we want, that means that the initial value problem that we have satisfies what is called the transversality condition. So we want our initial value problem to satisfy this condition so that we can go ahead and apply method characteristics, and we then will know that we can change coordinates from characteristic variables s and tau back to x and t and express our solution in the original variables. Now, the thing is, it is possible that this condition might fail at a certain isolated point, or it might fail everywhere. It just depends. So beware of that. And most problems are contrived so that it doesn't happen, but that's just it. It can, because your initial condition, your PDE, could be anything. Okay, well, at least I managed to get through all my notes. And, 2 minutes to spare.
Okay, well, since we've got time, are those all partials or some D's? Because I see it mixed.
They're supposed to be all partials.
Okay, that's what I thought. They don't matter.
Therefore this too.
That's what I thought. They look like legit D's.
Yeah.
Thank you.
Okay. Okay. So I guess it's probably gonna take a little longer to have these uploaded, but they'll still definitely be uploaded tonight though.